behavior of real materials is, of course, the idea that things expand. And let's start by talking about a solid because it's easiest to envision. Imagine I have a solid, a solid rod. And what that means is all the little molecules vibrate, but they don't move around. They're fixed in some kind of a lattice work. So if you've got a solid, you've got all these molecules that are in place and they're occupying more space than their own volume. Why? Simply because of their temperature. When you warm them up, they vibrate. If you warm them up more, they vibrate more violently and occupy more space. That's why when you heat things up, they expand. Generally speaking, it's not always strictly true, but generally speaking, if you heat something, it occupies more space. And the reason for that is simply because when you heat it up, you get more molecular activity. Each molecule occupies even more space than its own volume. So, as a rule of thumb, remember this is not like a law of physics, but this is a rule of thumb. As a rule of thumb, generally speaking, the change in length of anything is equal to the initial length, some constant, delta T. Sure enough, there's a constant, something like specific heat. There is a constant in there that reflects the particular material. You probably know that some materials expand more than others. A good example is metals tend to expand more than, let's say, ceramics. If you take two objects that are identical shape, let's imagine it at room temperature, 20 degrees C, you have a bar of metal and a bar of a ceramic material. Heat them both up from room temperature to, say, 100 degrees C. The bar of metal will grow more. That's just simply reflected in its coefficient of thermal expansion. So things expand when you heat them, and they generally follow this rule. I think on Friday we happened to mention that there is one substance, a celebrated substance, that does not always follow this rule in one specific temperature range. What material, when heated, shrinks in a very small temperature range? The celebrated material is what? Water. It's water, of course. And do you know the temperature range where if you heat it, it shrinks? 0 degrees to 4 degrees Celsius. You heat it up in that range, it shrinks. You cool it down in that range and it expands. What's the proof that water expands when it freezes?
Shatter a water bottle in your fridge.
Shatter a water bottle in your fridge. That's a good example too. I wasn't thinking that, but that's also a good example. The other one is ice floats, right? If it wasn't true, then when you made ice, it would be more dense than water, it would sink, but ice floats. That shows you that ice is less dense than water. Or, yes, freezing a glass water bottle in your home refrigerator will break the bottle, so show you that it expanded. What I would like to do is I'd like to talk a little bit now about the increase in area. Imagine I have a plate, perhaps it'll be a metal plate, some plate of steel or something like that, which of course has dimensions. Perhaps this is length and this is width. And of course it has the original area, length times width, like this. Now imagine somehow I'll just fix this corner right here and I'll heat the thing up. The reason I fix the corner is to make the picture simple to draw. That's the only reason I fix the corner. Now I raise the temperature, of course this thing is going to expand. It's going to get a little bit wider and it's going to get a little bit longer according to our relationship over here, right here. So we're going to have a new area, which I'll call perhaps A prime equals A naught plus delta A, where delta A is represented by the new area in here. A naught is, of course, the original area, and this is the delta A. So the new area, A prime, is going to be the sum of the old area plus the increase in area. And my interest is to find an equation for delta A. Delta A is the question here. So let's try to figure it out. Well, it's actually pretty easy because, of course, if this is W naught, then this will be delta W. And if this is L naught, this, of course, is going to be delta L. So that's going to be really easy to do. Let's start with this. A prime is going to equal, what do we see, length times width? So it's going to be L naught plus delta L times W, which is W naught plus delta W. Easy. Let's write in the necessary details. L naught plus L naught alpha delta T. This one is W naught plus W naught alpha delta T. It's the same material, so it's going to have, of course, the same alpha. And then what does they say in algebra? Foil, right? Yeah, foil it. Let's foil it. Which means simply this times those two, this times those two, add them all together. So we have L naught W naught plus L naught W naught alpha delta T plus W naught L naught alpha delta T plus, then the last two, right? We have plus L naught alpha delta T W naught alpha delta T. Great. Looks wonderful, doesn't it?
Now, what's the alpha mean?
The alpha means the specific material that it's made of. Just like the specific heat in calorimetry, alpha is a constant value that reflects the material. It's a number that you look up. It's a number that is measured primarily in a material science laboratory. So it's a number that simply reflects the material. You look up alpha for steel, if it happens to be steel, or ceramic, if it happens to be ceramic. It's just a number that reflects the material it's made of.
Okay, how did it just suddenly appear? Why isn't it in the beginning?
Well, it didn't suddenly appear, it appeared here. Here's where the suddenness happened.
Okay.
It wasn't sudden up there. I guess it was sudden over here. All right, so we have an A prime, A naught plus delta A is equal to this monstrosity here, although we'll notice that these two characters are identical to each other, aren't they? Mm-hmm. So we have L naught, W naught plus, and we have 2 times L naught, W naught, alpha delta T. And then here we have an L naught, W naught, alpha squared delta T squared. So we have L naught, W naught, alpha squared delta T squared. So far, pretty neat. Furthermore, you'll notice here that A naught is this term right there. So we can conclude then that delta A is just the other 2 terms, which I'm going to write a little bit differently. That is A naught twice alpha delta T plus A naught alpha squared delta T squared. Now let's try to figure out what these 2 things actually are physically. Well, this term, which comes from here, is just, let's look at this, L naught, and then this is delta W. So this is L naught delta W, and this is W naught delta L. So, to figure out this term right here, this term, we have to work backwards, and we see that it's the sum of these 2 terms. But L naught delta delta W is this area right in here. This is L naught delta W. That's what this area is. Let's shade that in some color. I've got orange in my hand, we'll shade it in orange. So, this term, L naught delta W, is the orange shaded area. The second term, W naught delta L, well, here's W naught and there's delta L, so it's going to be green. It's going to be this area. You can see this is W naught delta L. It's what's shaded in green here. It was shaded in green there. We're getting green shading now. That's this term. Apparently then, this little corner right here, whose dimensions are delta L by delta W, delta L by delta W, apparently that's this last term. But of course it is, because you can see this is delta L, this is delta W, and that's what the last term is. So, delta L, delta W is this term. So we have, for delta A, the sum of these two areas plus that area. Of course that's what delta A is. Now my argument is, in most cases, alpha